We have talked about all of the major celestial bodies. We have talked about theories we've talked about the standard model for how stars are formed and how they die. Of course, these have lots of open questions in them, and I'm sure these stories will evolve as we learn more. Today, we're going to hopefully make it through the concept of galaxies. In all reality, we will probably just make it through our own galaxy. And understanding our own galaxy is important. It will teach us things that we need in order to comprehend the cosmology, which is what we're working towards, the standard cosmology that we have, which is, of course, the Big Bang cosmology. So understanding how galaxies behave is at the core of that, because the eventual conclusion that cosmologists have arrived at is that the galaxies are all rushing away from one another. And this is, of course, the primary argument for the Big Bang theory, which is where this class sort of terminates at. Yes?
I'm sure you saw the studies that were published recently about how there's galaxies that would kind of betting that their existence kind of disprove the universe of 14 billion years old.
Yeah, of course, yeah. So the question was, what about these galaxies that are older than the beginning of the universe? And I'm gonna get into a lot of depth with that when we get to the Big Bang theory, yeah, because I think that there are some serious questions going on. There's other questions too. The proposed acceleration of these distant galaxies as they move away from us, depending on how you measure it, right? If you measure it with the CMB, you get one value for this expansion, and if you measure it by this redshift, you get a different value. And the values are really tight measurements, but they're not similar at all. They're many standard deviations away from one another. So there are a lot of contradictions, but before we get to that, I think we should try to understand why people even came up with this Big Bang thing in the first place before we start to kick it too much, because it's important to understand where these people are coming from. And so I hope that by the time we're done talking with galaxies, you understand at least why people came up with this Big Bang business. And then we can talk about the potential ways that it'll change and alternatives to it as well. One thing is for certain, we'll work towards this, but it certainly does appear that things that are really far away look very strange. And they look very strange in that they're very red, and that if you take that reddening to mean that they are moving, if we take it as a Doppler shift, which is often what we do with reddening, then they appear to be moving away from us. But we'll play with some different ideas for what else that could mean. All right, so anyways, I gotta step this back. So we'll probably mainly today talk about our Milky Way. And it might come as a shock, but people essentially until very recently believed the Milky Way was the entire universe. People thought that the other galaxies they were seeing were just little clumps of gas, little nebula. So we're going to check out the history of our own observations and the debate that went on. Then we'll look at the structure of our galaxy. Since it's the closest one to us, it's the easiest one to interrogate structurally. And then we can apply that to all of the other galaxies as we move out. We'll also talk about basic formation models, although obviously we can't see a galaxy forming. If you thought trying to understand how planets form or stars form is difficult because they take millions of years, at least, well, then the galaxy is going to be much worse because, of course, this is an agglomeration of lots of stars and lots of planets. I don't even know if lots is a big enough word for it. So now, everybody here have you all seen the Milky Way go outside at night? Yeah? So everybody on Earth has been seeing the Milky Way for a very, very long time. It's worth pointing out, I would hope to go into some of the more ancient stories of the Milky Way, but I don't think we have time on account of the snow day that we had. So I have to save that for next year. But I do want to mention that one of the first pieces of writing we have about the Milky Way comes from the Sumerians. And it's interesting because the story they tell of the Milky Way is very much a dragon slaying story, which should fit in nicely to the lecture that we did on how the stars were seen by the ancients. Of course, in this epic poem, the Milky Way was essentially created from the severed tail of this dragoness named Tiamat, who was slayed by the hero Marduk. So I think that's somewhat relevant, that the central story that we keep seeing over and over again has to do with this concept of beating something down that's dark and not understandable, and this is the main story that's told. Of course, the Milky Way is one of the most visible structures in the sky, beyond individual stars, say, or Venus, something that's very bright, the moon, the sun, and of course you have the Milky Way. And people who live, we're lucky out here, we can see the Milky Way quite well, especially on a clear spring night or something. People in the city probably have no idea that this big swath of stars is stretched out above their head, so we can count ourselves lucky now. Yeah, I'm gonna have to skip this story from the Quechua Indians, but people since antiquity in the West, people, I'd say starting with the Greeks, people started to actually come up with more scientific mechanistic explanations for what this phenomenon was. And many of them, almost none of them supposed that it was a lot of stars, actually. This was kind of beyond people's imagination. So the first Greek philosopher to write about it was Anaxagoras and Democritus. And we've talked about Democritus before because Democritus came up with the idea of the atom. And this was, 400 BC, so 2,500 years ago. And Democritus had this idea that the Milky Way is the glow of stars, but they're not directly visible because of the Earth's shadow. So while they believed that essentially all the stars were being illuminated by the sun, but the Milky Way was sort of this apparition caused by the Earth passing in front of it. Which is interesting because actually the Milky Way, if you notice, you probably see the bright region of it, but actually on a very starry night, the Milky Way off towards the edges of it is quite dark. It makes a very banded, cloudy structure. Of course, this is from all the dust that we've been talking about. Aristotle came along a bit later than that and proposed that it was actually an atmospheric phenomenon. And this was Aristotle, it's hard to underscore how important Aristotle was to the people who came after him. But this proposal was taken very seriously all the way up into modern times. And, I think that was the main idea. Now, coming out of the Muslim world were some perhaps interesting arguments against that. So this was maybe 1000 AD-ish, so 1,000 years ago from us, or I suppose, yeah, well, more than 1,000, but somewhat more modern than the Greeks. And the Islamic scholars actually proposed that, if this was the case, that the Milky Way was an atmospheric phenomenon, in other words, if it was something in front of the moon, that there should be interference with viewing the moon, first of all, and furthermore, you should have parallax effects, right? Where depending on where you're at on the Earth, you should see different things. And of course, this wasn't seen. So that was kind of the first significant criticism. So the Persians actually developed that a bit further, and this was kind of the first time that people resurrected the idea that actually the Milky Way is countless stars or star fragments, which was quite prescient. And it didn't come until Galileo actually made use of the first telescopes, which were actually developed by the Dutch, the first telescopes. But Galileo pointed them at the stars and actually was able to see, Galileo did not actually detect the stars, but he did see that that there were some stars in the Milky Way. Now, he was also convinced that the blurring, the idea that the Milky Way was this stream, was some sort of atmospheric refraction event, and I think this was a holdover from Aristotle. But he was one of the first people to note that there were some individual stars, at least among it. Flash forward a bit further, Kant, whom you've probably read about if you're taking any philosophy courses, actually proposed that the Milky Way might be a rotating body comprised of innumerable stars that are held together by similar gravitational forces to the solar system itself. So this was the first time that anyone proposed that it was essentially a disk-like object, so similar to our own solar system, which is quite interesting that it came from a philosopher and not from an astronomer. They also very presciently proposed that there might be many of these galaxies out there, right? Just like it was kind of an old idea that there would be many stars with many worlds surrounding them. These guys took that idea and applied it to galaxies as well, which was sort of laughed off the table at the time until the 1930s, when people actually began to make these detailed observations with these huge, multiple, I don't know how big these telescopes were, but huge lens telescopes back in the 1930s, particularly Edwin Hubble, who, of course, we know from the famous Hubble telescope at this point. Now, the first person to actually start to detail the individual stars amongst the Milky Way was this gentleman named William Herschel, who we mentioned briefly when we were talking about the solar structure. And he actually tried to produce a diagram of these, and he did a pretty good job of it, actually. Now, there was people who came along and looked at this, and they started looking towards Andromeda, which we, of course, know now as a separate galaxy. And this gentleman named Herbert Curtis pointed out that there was actually nova, right? I'm not sure they were supernova, but stars blowing up, and that they appeared to be concentrated in these nebular regions, what they used to think of as spiral nebula, right, which we now know are separate galaxies. And Curtis made this really interesting point. He was like, why would all these nova be concentrated in one region of the Milky Way, of what they thought was the universe at the time? That didn't really make sense unless they were entire galaxies by themselves. And so he championed this idea of island universes, right? There was lots of different, what they called universes at the time. And that was a very compelling argument, and people debated that for a long time. So there was famously a huge debate in the 1920s about this with a gentleman named Shapley, who was arguing in favor that the Milky Way was the entire universe, and of course Curtis on the other side. Herbert ended up actually winning this one out, but it wasn't the end of the argument. So this continued for something like a decade, and let's see. Okay, so eventually Curtis actually was able to point out that the radial velocities, now if you guys remember when we talked about radial velocities, essentially if you look at something that's rotating, one side of it is going to be coming towards you while the other is going away, right? If you're looking at, say, a planet orbiting a distant star, you can, or let's say, you can actually, that's difficult to say. So if you look at two stars orbiting one another, right? As one is moving towards you, it's going to be slightly blue shifted, and one that's moving away is going to be slightly red shifted. This is a basic Doppler effect. And they applied this idea to these nebula, these distant nebula. And Curtis essentially ended up winning this debate because he pointed out that the radial velocities of these spiral nebulae was just too great. They couldn't actually be attached gravitationally to the Milky Way. There's no way they would be able to be pulled away that way if they were just swirling clumps of material and dust. So finally, in the end of the 1920s, very close to 1930, Hubble was doing these was working on some of the bigger telescopes at the time, like I mentioned. And he actually started looking at those variable stars, which we talked about way back at the beginning of the course. And you'll notice that you might recall that variable stars are kind of the key to understanding distances when we're talking about really far away objects, because this very brilliant lady at Harvard at the time had deduced that there was a very tight relationship between the period, that how fast these things pulsed, and their luminosity, their absolute surface brightness. And as a result of that, the idea was that you could extend any observations of variable stars, these particular Cepheid-type variable stars that had a very neat signature to them. And if you could see those and measure their period, then you knew exactly how bright they were. If you knew exactly how bright they were and you compared it to how bright they looked, then you could get the distance to these far-off objects. So Hubble applied this technique to the variable stars in some of these satellite galaxies to us. We now call them the Magellanic Clouds, right? And these are tiny little galaxies. Actually, I think I showed them on the previous slide. Let's go back and look at them really quick. Right? So there's our Milky Way, and there's these tiny little ones right at the outskirts of us. So they were looking at those. And what they figured out was that it turned out that Andromeda and these satellite galaxies were just way too far away based on these Cepheids. This is, by the way, the period luminosity relationship up here. So yeah, we can thank Henrietta Leavitt for that. Actually, Leavitt, by the way, I'm not sure I got to mention it in this course. I know we talked about it last semester. But Leavitt was actually hired along with a number of ladies at the time. They were actually called computers, right? So their job was to essentially tabulate and calculate all the measurements that the astronomers had done during the night, and they would get all this data and crank it out. So the original computers were actually a large group of women at Harvard, which is quite fascinating. And they ended up doing a great deal of the legwork and the theoretical side of things as well. All right. So let's see here. We got to keep moving. Eventually, Hubble was actually able to resolve those distant nebulae, especially the Magellanic Clouds, into individual stars and actually start to make charts that showed those things. Now, in terms of understanding the structure of our own galaxy, this is a tricky thing to do, right? Because, of course, all that interstellar dust, the shadowy stuff that we see when we look out there, prevents us from seeing very far into the disk when we look out into the Milky Way, right? We can't see it at visible wavelengths. We do, however, have this nice 21-centimeter hydrogen line that we talked about a while back when we were talking about the best way to observe these clouds. And it turns out that this is quite nice because the 21-centimeter line, this particular wave of emissions from these hydrogens is relayed right through these clouds quite nicely. We can observe it. We also have figured out how to do infrared studies now that we can go to space, so we can look at the heat signatures, and those also can be seen through clouds of material as well. Of course, to do infrared observations, you got to be in space, right, for the most part. The heat from Earth would just tank your observations otherwise. And actually, this is one of the biggest problems with these giant telescopes like James Webb and the Hubble Space Telescope. The problem is keeping them really cold, right? Because if you want to observe heat signatures, the observing instrument itself has to be very, very cold. And so that's one of the trickiest parts, actually, about building a telescope in space, it turns out, is keeping it shielded from the things that might keep it warm, like the sun. We also were able to eventually do some radio observations of the disk's gaseous components. And we figured out pretty quickly that there was essentially two major spiral arms in our own system. And you can see them up here. You have the Centaurus arm and the Perseus arm. Now, there's some smaller spurs, too, which are important to us, particularly this Orion spur, which is where we're found. And it's about 10,000 light years long, so it's an enormous neighborhood that we live in here. Let's take a little closer look at it. So there you get a little better picture of the Orion spur, which we call home. Now, the general structure we've kind of hinted at so far, there's essentially a thin disk, a thick disk, and a stellar halo, which you can see here. And we've talked about these different clusters that are around the globular clusters that surround us. So the thin disk of stars is embedded in a thicker disk, which is actually more diffuse older stars. The thinner disk is, of course, where we think all the younger stars are coming from. And this extends something, the thicker disk extends something like 1,000 light years above the central midplane. And it's much more rarefied, right? It only contains something like 5% of the stars, which are the survivors, essentially. Now, if you close in on the galactic center, there's this thing we call the central bulge, which is interesting. And we'll talk about the structure of the central bulge a bit, because the center of the galaxy is a topic of heated debate. Strange things appear to be happening there. And actually, the motion of the galaxy in general is a bit of an open thread in astrophysics and astronomy, right? And we'll talk about that. I really hope we get to it today, because, we've essentially tried to explain all of our observations about and all of our theories about how the galaxy behaves and how stars behave and how all of these processes behave were fundamentally rooted in theories of gravitation. Gravity being the only force that people were convinced could explain the motion of these large-scale structures. But our theories of gravitation kind of fail is the problem, right? They don't actually do a good job of explaining how the galaxy is held together and how it moves. And they fail so bad, actually, that at this point we have to invent a completely unobservable substance which hangs out in the outer regions beyond the halo, or I suppose looping around the halo, because that's the only way that we can gravitationally make sense of the way that this galaxy works. So there's a lot of work to be done there at the very least, and we'll talk about this concept of dark matter in detail in just a moment. What else do I want to say about this structure? I think that about covers it. Let's look at how this, this is, of course, when we're trying to understand why galaxies have the particular structures that they do, of course, all of the modeling, again, begins with gravitation. And, let's entertain that idea that gravity is behind all of this, and then we'll eventually work our way towards some other propositions as well. So, the basic idea is that the galaxy doesn't rotate like a perfect disk, like a frisbee. Instead, individual stars are actually orbiting around the center of the galaxy, more like a solar system. Now, in this case, objects that are further away from the center would take longer because they have less gravitational influence than the ones that are closer to the center. So we call this differential galactic rotation. Now, so the idea, of course, being that if these two masses approach one another, then they're going to begin circling around their center of mass, and eventually you get this spiral shape. Now, the problem is that the concentration of matter in the arms should be sufficient to hold the arms together, but it turns out that it's not, right? In reality, if we apply that model, and we apply a simple, basic gravitational model to the structure of these two balls of stars or balls of gas meeting one another, we should end up with something that looks like this over here. And the reality of the situation is that it looks more like this. So this is kind of hard to see the difference, but the one on the left, you can see the interior is actually rotating much faster than the external areas, right? Over here, what we actually see is that the galaxy kind of rotates as one giant object, more or less, right? So we're looking at the velocity curves over here. This is velocity versus radius, and I'll show you a bigger version of this graph on the next slide. But in reality, the velocity remains quite constant as the radius, as you move away from the center, radially from the center of the galaxy. Now, I would say this is one of the most perplexing questions in all of astrophysics, actually, right now. And of course, I've sort of hinted at the solution that is on the table right now, which I would say almost no one's happy with, which is this idea that there's just an invisible substance that is pulling the arms essentially out at the limb. Actually, it's not a small amount of substance either. It's a tremendous amount, right? I think that it rivals the amount of substance in the galaxy itself. But I'll pull those figures up for you in a minute. So, and there's some different proposals for how to rescue that as well. Okay, let's look at this light curve a little bit. Or sorry, this rotation curve. Okay, so here you can kind of see the predicted, which is in blue, versus the actual in red. This is the radial velocity. So the galaxy has got to have more gravity than can be supplied by the things that we can see, if gravity is what is actually keeping the galaxy together. And if gravity isn't what's keeping the galaxy together, then what is, right, is the real question here. Okay, here we go. So, you know, if we actually calculate the amount of material that's missing, the amount of dark matter that should be present there, it's something like 20 times the amount of matter that we actually are aware of, that we can see, that's luminous, right? So it's not a small problem, right? There's not just a little bit of error in our gravitational assessment of the galaxies. It's pretty broken, actually. So, you know, most of the people who are working on this problem are actually thinking, well, maybe our model of gravity is wrong, actually. The problem is that a lot of these people, and there's a few different theories that are actually being more or less entertained in mainstream cosmology, at least within universities. One of the more popular ones is called MOND, which I think is called Modified Newtonian Dynamics. Most of these alternatives to general relativity, they also introduce some sort of, you know, nebulous constant or field. They don't really actually make any better improvements in my estimation. They don't actually explain the gravitational phenomenon better than Einstein or Newton. And of course, that makes sense to some extent because Einstein and Newton really just described how gravity appears to behave. They didn't really explain why it does that. So, you know, this is a huge problem. I actually had a friend in grad school who was working on a dark matter, trying to do a dark matter detector, build one in the physics department at Columbia. And he ended up actually leaving that lab because he felt it was quite hopeless, actually. You know, trying to detect something that nobody has succeeded in detecting for decades makes for a very difficult graduate project. So there's only really two options. Either there's nothing there, or there's something there which we don't understand, right? There may be some sort of exotic material that doesn't interact with light that we're not aware of. This is, of course, what most popular media latches onto. There could be something really cold out there that we can't see. At any rate, we can sort of model where that material should be. And there's huge... There's no shortage of modeling to describe the swirls of this proposed material and where it should be. And of course, people have ruled out as much as they can. And they say it can't be a gas, right, because we don't see that 21 centimeter line. It can't be ionized hydrogen because we'd see visible radiation. It can't be neutral hydrogen because we'd see shadows, essentially. We'd see shadows in the ultraviolet spectrum. It can't be anything crazy like black holes or neutron stars because we would see X-ray radiation from it. And it can't be, well, we'll talk about that object in a second. Now, one proposal that I think is kind of interesting, so your textbook, I just want to quote your textbook, says that brown dwarfs and lone Jupiter-like planets have also been ruled out. I don't think that's totally true, actually. So there's a proposal on the table called Rambos. Let's see, what does Rambos stand for? Essentially, these are massive objects that are made out of clusters of something that is actually quite dense, right? And this is actually being entertained in the academy to some extent. They could be very long-lived cold objects, right? Which I think is an interesting proposal. I think a lot of our mysteries that we've encountered so far could be solved by very cold, old objects. But this again gets us into the problem of how old is this universe? Is it old enough to make very cold things, right? And of course, the cosmologists, they're still hanging on to the idea that, for the most part, that it isn't old enough for that to have happened. And we'll see about that as observations continue to come in. Certainly things appear to be older than we thought they would be. And actually, I think one of the more troubling observations, I would say one of the things that's troubling astrophysicists and cosmologists most about this James Webb data is not that the galaxies they're finding are too old, although some of them definitely are too old. The problem is that the galaxies that they find at the so-called early days of the universe are totally the same as the ones that are around here right now. And this is most troubling because what they had expected, according to their Big Bang theory, was that they would see a lot of primordial goo, right? They would see a lot of early galaxies that were just starting to form, right? And this isn't the case. They don't actually see anything like that. They see perfectly formed galaxies that look absolutely normal. I actually think that a lot of this confusion could be rescued if you just remind yourself and anybody that you're having this conversation with that the word universe to astronomers just means everything we can see, right? And many astronomers, and certainly many popularizers of science, have taken the word universe to mean everything in existence, which I think is a totally reasonable way for you and me to think about the universe on a daily basis, but it's not what astronomers mean by universe. So if you're talking about these distant observations, these early observations, what you really mean is the things that are at the edge of our ability to see. And that puts you in a very different position to understand concepts like birth of the universe. What does that mean? Well, it means the beginning of what we can see. Right? That's a very different concept than a creation type event. All right, so Rambos, maybe. I also had this really fascinating conversation over the weekend with this Princeton astrophysicist named Eric Zernstein. And Zernstein studies the structure of our heliosphere. And I think we talked a bit about the heliosphere in this course. But the heliosphere is essentially the boundary between our solar system and the next. That's an easy way to think about it. It's a bit earlier. It doesn't bump it itself, the heliosphere, which is essentially a bunch of ionized gas that is basically, you could think about it as it's like the pressure boundary from where our solar wind is smashing up against the interstellar medium, right? So it makes this bubble. And as we move around the galaxy, the bubble sort of crashing in like a shock wave. If you've ever seen like a sonic boom or something, it's very similar to that. It's where the shock happens. But behind it, it trails this tail for, thousands of AU, like very, very far. Essentially, quite easily to the next star system, right? Now, beyond the heliosphere, there's actually a cloud of hypothetical objects. We can't see them because they're cold, but we think they're where all of our comets come from. We call this the Oort cloud. Now, what's interesting about the Oort cloud is that the Oort cloud actually extends halfway to the next star system, right? And presumably, the next star system has an Oort cloud too. And presumably, all of these Oort clouds are sort of mashing with one another, right? So I guess, and this was a really interesting conversation. Y'all should check it out. We actually haven't put it out yet, but maybe next week. What we were playing with in the conversation was what other processes could be engaging the solar systems with one another. Because if the solar systems are able to, in some sense, Velcro onto one another through other processes besides gravitation, right? If there's actual enmeshment of their various structures, then you're moving into a paradigm where there are additional forces that can hold the galaxy together besides just gravity, right? Because the reason we end up with this dark matter stuff is not because we've seen it, it's because we can't explain the cohesion of the galaxy without a bunch of, we can't gravitationally explain the cohesion of the galaxy without it. So, like I said before when we were talking about black holes, whenever you hear this dark word or black or anything like this in science and in astrophysics, whenever you hear of singularities or infinities, these are 100% historically situations where we don't understand something fully and we're not incorporating variables that we need to be incorporating into the picture. And so, you know, as tantalizing as the idea of these super magical substances and super magical objects is, I'm sorry to break your heart, but they will almost certainly go the way of the dinosaurs eventually. That's just the way that science works. We don't understand something, we put a filler in there until we can work it out later. But I guess the paradigm that the solar systems do interact with one another is quite interesting to me. Yeah?
Oh, so does that mean since black holes have been proven to be like a real thing that they may just have, you know, a different name later?
Yeah, I mean, well, so the question is, since black holes have been proven to be a thing, might they have a different name later? I would say, well, I gotta pick that question apart a little bit. So proof is a strange word, first of all. You know, there's two different uses of the word proof. One I can think of is in mathematics, where you have a series of assumptions, let's say some identities that you lay out on the table. You know, if A equals B, B equals C, then A equals C. This is an identity, right? So you have these axioms that you apply to some statement, and you can prove out certain logical conclusions that must result from your initial statements, okay? The other use of proof is in something like court, right? Where you have to essentially convince some jury that some series of events transpired, let's say. And what you're saying, I think, when you say the word prove, since black holes have been proven to exist, well, I think what you're saying is that the jury has been convinced that these objects, this appearance, something strange is happening. There's points in space that don't have luminous bodies, which have X-ray emissions. They have gravitational things are circling them, let's put it that way. And if gravity is at play, then the object there must be so immense that it has crossed over the boundary conditions of Einstein's laws, and it should essentially have collapsed into itself, right? Now, if we start to understand other processes that could play into the motion of bodies in the cosmos besides gravity, right? If we start to extend the length of the universe and we start to imagine how cold things could actually be invisible but playing into the dynamics, maybe even gravitationally, right? As we update our understanding of how what processes contribute to the motion of the bodies, then perhaps more than just the name will change, right? Maybe the name will stick around because people love the name, I don't know. But maybe the understanding of what it is will change. So I'm not sure if that answered your question totally, but you know, just like I think that it's really important, I think it's really, really important to remember that less than 100 years ago, well, I suppose it's about 100 years ago now. No, less than 100 years ago, let's say like 95 years ago, people believed the Milky Way was the entire universe. That's how fast this field is changing, right? So it would not surprise me in the least if 100 years from now we have a completely different understanding of how these processes work. And this will just be kind of one step when some astronomy professor is sitting here 100 years from now, hopefully this place is still here, he'll be telling a very different story. And the dark matter concepts, black holes, they'll be a bullet point in that story, but there will hopefully be a better understanding at that point. All right. So, you know, stop and think about that for a minute. If the central theory of how galaxies are held together comes down to gravity right now, but 95% of the gravitational material is not there. We can't see it, right? Just let that sink in for a second. All right, so the center of galaxies is quite interesting as well. You know, at the center, we also run into this problem where the dynamics at the center seem to indicate that there should be a massive, massive object upon which all of these other stars are being pulled around, right? Something like 4 million times the mass of our sun should be sitting right at the center of this thing and squished into a sphere that's something like the size of Mercury's orbit. So not much bigger than our sun. Now, we can't really see the center of our own galaxy in visible light because there's a lot of interstellar dust. And that makes things tricky. So we're looking in infrared and radio radiation. Actually, there's so much dust that all of the light coming from the center of our galaxy is dimmed by factors of around 1 trillion, like 10 to the 12th, which is crazy. So we have a really, really obscured view of that. So we're looking in infrared and we're looking in radio waves. Now, there is this nucleus, this place right at the center does have a radio signature to it, and we give it the name Sagittarius A, mainly because it was visible in the Sagittarius constellation. And there's been a fair amount of work to detail what this whole agglomeration of stars looks like there and what could be going on. So, of course, what happens when you cram, thousands of solar masses into a tiny space? Well, you end up with something that starts to break down our understanding of physics, right? So the standard hypothesis is that there's this black hole at the center of this galaxy. And again, if gravity is the central player, this is a necessary conclusion. But I do think that it's worth considering that gravity might not be the central player here as well. So this we have here is a radio map. So this is in wavelength of 90 centimeters from this huge array of radio telescopes in New Mexico. And the Galactic Center is labeled there, Sagittarius A, right in the center. Now, this is a huge structure, so that little scale bar down there is showing you something that's 240 light years long. And you can see all sorts of other like substructures happening. There's these little bubbles, right, which you can see, which are thought to be supernova remnants, little filamentary structures. I mean, there's all sorts of architecture actually at play here, which is interesting because architecture in the everyday sense can bear a lot of tension, right? How does a huge part in designing these roof structures and the walls and everything is not just loading them from the top, right? But also that they can pull on one another. Their various pieces can pull on one another. So I think that in the future, these tensile structures must be considered. How these various we see these structures, these filamentary structures. These pieces, right, seem to be interacting with one another, and there probably is a lot more to it than gravity itself. So I'll expect to see that playing out in the next few years quite a bit. We can also see the Galactic Center in X-rays, which is what we have here. This is actually a mosaic made from 30 different images from an X-ray satellite that we have. The emitting points of these X-ray sources are thought to be white dwarfs, neutron stars, or something even more compact, right? Because those are the only bodies that we think are capable of doing these high energy emissions. So this is tricky too, because if there is actually this exotic form of matter, this black hole at the center, there's some problems with that too, because it doesn't really make any sense how there could be a bunch of stars sitting around a black hole that size, actually. So the question is, how are there so many luminous stars so close to a black hole and not getting completely devoured by it? Because we don't see them getting sucked up by anything at the center. And so this is a huge problem. It's also, possible, one of the standard explanations for that as well. They're just moving in there, right? They didn't form there. These these masses of stars came and they're just recently arrived there, so they haven't been interacting with the black hole yet. But I'm very skeptical. All right, so we can zoom in a little bit more here. Come on. And this is actually an infrared telescope here that we're looking at. And we can see this crowded region with all these stars. And they're actually undergoing orbits which are quite anomalous and eccentric, right? They're bobbing up and down above the plane. They're going in at all angles, which is quite interesting. So from these orbits, actually, is how we estimate the particular mass of that object, which we can't see at the center. And like I said, 4.6 million times the mass of the sun. And, there's a lot of interesting things to be considered there. Of course, I mentioned this last class, but one of the assumptions of general relativity, which is a very precise model of how gravity functions, but general relativity tends to treat masses as point sources. I actually talked a lot about this with Eric in the podcast this weekend too, because they do the same thing when they're modeling the heliosphere. They treat the sun as a point source, right? What has this much energy output and so forth, but it's all arriving from the center of the sun, right? And gravity is very much treated the same way, where all of this material is treated as if it's coming from one little point, right? But this is actually, I think this is a bit unfair because at the same time we understand that if you were to drill a hole to the center of the Earth and drop a ball down there, let's say, it actually wouldn't experience a lot of gravity at all, in the sense that it wouldn't be crushed into oblivion, because actually it would be being pulled by the matter on all sides of it, right? Actually, the gravity at the center of something would be actually quite low, which I haven't seen this adequately incorporated into a lot of these modelings because general relativity doesn't treat gravity the same way. It treats it as being focused at the point where all of the mass is centered around. So I wonder how much of these artifacts are a result of treating gravity as a point, coming from a point, as opposed to coming from atoms themselves. We don't have an atomic theory of gravity right now, which might surprise you. So general relativity is extremely successful at describing how things behave at the big scale, galactic stars, etc., planets. And quantum mechanics is extremely successful in predicting the behavior of very tiny things. But gravity, in terms of how atoms produce gravity, the contender right now is called a theory of quantum gravity, which is elusive. Nobody's actually been able to develop a theory of quantum gravity so far. So we try to, in some sense, ignore the fact that gravity must be being produced by atoms. And of course, the quantum mechanicists aren't really concerned with atoms. They're concerned with what's happening below the atoms, and they're looking for how gravity could be produced at those structures below the atom. But in all likelihood, I would say all evidence points to the fact that gravity is the result of atoms pulling on one another. And there isn't a robust theory that describes that right now. I think that the more that we understand what gravity is, the more some of these bizarre supernatural events can be integrated into something that's actually mechanistic and makes sense. I would say the same thing is the problem. We're going to start talking about light and redshifts here in a minute too. But remember, light, again, is treated as a point, right? It's not treated as an actual physical interaction between atoms right now. And this is perhaps problematic because if you don't understand something as fundamental as the thing that you're measuring in the first place, you just sort of you describe how it behaves, but you don't really understand what's happening, then your conclusions, of course, are going to suffer from the same lack of understanding. And I think that's how we end up in the weeds sometimes. All right, let's keep cruising. So, like I said before, all of the young stars are in this thin disk. One thing that's quite interesting is that the thin disk is rich in metals, and they orbit the galaxy center at this is, by the way, we're still talking about the center, at high speeds. Now, the stars outside of the center in this halo are thought to be quite old, and they have low abundance of the heavier elements, right? which is interesting. And the way that we've explained this to ourselves is that the younger stars are recycling the corpses, let's say, that's kind of graphic, of these dead old stars. It's very hard to not apply biological analogies to these things. So the halo stars do sometimes dip down through the disk in the central bulge, and there's undoubtedly interesting interactions that occur there. But so the stars that are in the thick disk, which are moving in and out, are thought to be intermediate between the two extremes. They're not old, they're not young, they're somewhere in between. So this is probably a good point to mention that in general, we think of there being as two populations of stars in the galaxy. And this is actually determined by this gentleman named Walter Beatty. I don't know how you spell his name. Say it, B-A-A-D-E. Batty? I like Batty. All right. So he called the bright blue stars in the spiral arms population 1, and he called the stars in the halo and the globular clusters population 2. So population 1 stars are only found in the disk, and population 2 stars don't really have any correlation to their location, to the location of the spiral arms. And this will play into some of our dynamics about when we talk about distant galaxies and what we're actually seeing, because the funny thing is when you look out into very far off galaxies, you can't really resolve individual features so well, so you're kind of blending together these two populations. So our sun is a population 1 star. It's got a fair amount of those heavy elements, things that are bigger than hydrogen and helium, something like 1 to 4% of their total mass. Whereas population 2 stars have so little of that, it's something like 1/100th the concentration that we have in our own sun. So those are thought to be essentially first generation stars that are just cooling very slowly. They're still hanging on. They weren't massive, so they didn't go through their life very quickly. Let's keep going. So there's a few hot young stars in the central bulge, but most of the bulge stars seem to be older than 10 billion years. And what's strange is that unlike the halo stars that are the same age, the heavy elements in the bulge stars seems to be about the same age as the sun. Now, that's a tricky one to explain, actually, in terms of the formation models of the galaxy. The best guess right now is that there was all of these supernovas from the first generation of stars, and that they were essentially, all of the material from those was essentially swept up by the inner material at the bulge as a result. And so it gave them a good supply of heavy elements despite the fact that they're quite old as well. So this happened very much in the early days of the galaxy's formation. Now, the formation ideas about the galaxy are if we hardly understand how planets are formed, if we hardly understand how stars are formed, then understanding how the galaxy is formed is one level deeper into the uncertainty territory. But we have some theories about that. And essentially, the idea is not too dissimilar from what we've already talked about with our other disks, our solar systems and our planets and all of this. I mean, the basic idea is the same one that Kant proposed and Laplace developed for the solar system back in the 1700s. Something like the gravitational forces cause the gas in the thin disk to clump together, and that this whole thing starts spinning together, and eventually you get a contraction of masses, and you get something that looks like the galaxy. I don't want to spend too much time on this. It's a little bit dissatisfying because, of course, we know the galaxy doesn't really rotate the way that it should if this were the case. So I think that if anybody wants a topic to study for the rest of their lives and become a scientist, galactic rotation is where to go for sure. And this is called the monolithic collapse model, by the way. So there's an alternative. A multiple merger model might be a little bit closer to how things work. In the multiple merger model, you actually have something like the monolithic collapse that does give some spin and cohesion to these galaxies, but over the eons, the galaxies are messing with one another, right? In fact, we can see that this really nice galaxy, Andromeda, which is sort of our, I guess it's our nearest fully formed galaxy. It's a nice spiral galaxy. It's rushing towards us, actually, which means that in some billions of years, it will actually collide with us. And we see examples of galaxies colliding all the time. But in terms of our own galaxy, certainly there are these clusters, right? There's some of these satellite galaxies which are stretched out in such a way that indicates that they're actually interacting with our galaxy directly, either gravitationally or different sorts of collisions or frictions between their subcomponents. So there is evidence that the galaxy's interactions with its neighbors are actually giving it its shape to some extent, and I think that's probably a safe bet. But to what degree that's playing into things we don't really know. All right. Yeah, this is just another illustration of that same idea. There's going to be tidal forces, right? As these distant galaxy or sub-galaxies, what do we call them? Satellite galaxies, as they make their way around, they're going to actually cause effects sort of like the tides on Earth, right, with the moon. As the moon goes around, it's going to affect the water in our oceans, pull it around, push it around. Same thing is going to happen as these satellite galaxies make their orbits. So there's all sorts of processes that could be giving our galaxy some shape that we otherwise wouldn't have. I don't know about cohesion, but certainly sculpting it. This, by the way, is one of those little satellite clusters. This one's called Sagittarius dwarf galaxy, which is the one that we think is circling and merging with the Milky Way right now, which is quite a ball of stars, actually. What do we want to say about this? Let's look at some mergers, actually. So this is pretty cool. These are projected interactions of our galaxy with Andromeda as it closes in on us. So the thought is that 3 or 4 billion years from now, that in the sky we'll actually see something like this coming towards us, if we make it that long. That's a long time. Yes?
How long do these normally, like the collisions normally take? And like, if it's a really long time, how exactly can we tell that the Milky Way is merging with that dwarf galaxy?
Yeah, it's a good question. So the question is, how long does this take, and how do we know how long it takes, essentially? Well, we're gonna get into that. We're gonna get into that in some detail in the next part of this. But the basic idea is that when something, we apply this Doppler principle, right, to determine the motion of luminous bodies, right? And it's very much the same idea I think it just can't be restated enough, but essentially, like, think about something like an ambulance passing you on the street. As it moves towards you, the frequency of the siren is actually going up, and as it moves away, the frequency goes down. So it's like, woo, 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 right? Well, that's because as it moves towards you, I mean, from a relativistic standpoint, you may as well be moving towards it. And as you're closing that distance between the two of you, you encounter more wave crests per unit time, right? Which it gives you the illusion that the waves are shorter. In reality, you're just encountering more of them. And so the same idea is applied to stars as well, this Doppler idea, that when you're moving towards something, or it's moving towards you, it's going to be bluer, right? Because the waves are going to be perceived as being shorter. And then as it moves away, it's going to be redder. So Andromeda is actually blue shifted, and we can calculate a velocity as a result of that. So, things could change, though, also. The problem is there's other things that can cause bluing and reddening. There's a very famous astronomer named Halton Arp who made his career of sticking thorns into the sides of the redshift cosmologists by pointing out all of these active galactic nuclei that were shooting streams of particles in the direction of our field of view, very fast accelerated particles that actually had intrinsic redshifts to them. So they were redshifted, but it couldn't have been a result of motion. And so he made a real stink over at NASA and all of these places by pointing out, just cataloging. I think they actually canned him eventually. He didn't make a lot of friends. But he pointed out that there was a huge catalog of events that we could see in the cosmos that were redshifted anomalously. And so he said, I don't think that this theory that Doppler shift is behind redshifts is fair. And so that debate is sort of ongoing. Although for the most part, I would say 99% of astronomers stick with the idea that when you see a redshift, it's a result of the Doppler shift. So, yeah, we think that it is rushing towards this. Now, 3 or 4 billion years is a long time. There's also a lot of space in between each one of our solar systems, right? If you actually think about the amount of material that is packing up this place right now, when we think about our solar system, it's mostly empty space. When we talk about the last semester, when we talk about the asteroid belt, most people have this idea of the asteroid belt from Star Wars or something where like you're dodging all these asteroids everywhere. But in reality, NASA doesn't even blink when they send a probe through the asteroid belt because there's something like 100,000 kilometers between each one of those asteroids. So it's very hard to hit one, actually. If you want to hit an asteroid, you have to really, really aim for it well. And so there's reason to believe that even though these galaxies might interact, they might even pass through one another, there's probably very little direct collisions that result from that, which is kind of perplexing, but I think you have to really, really factor in how not dense these regions are. Now, their satellite, like their gaseous, their heliospheres might interact, their Oort clouds might interact. There might be these ancillary interactions, but the planets probably aren't going to crash into one another. And of course, it's passing through rather slowly. I'm sure that will take billions of years too. I don't think it will be end times, but understanding how those processes transpire might give us more insight into why even the galactic rotation problem, right? It might actually, if the universe is not 14 billion years old, but let's say, let's just take the other extreme. Let's say it has no age whatsoever. It's always been here. Well, then that's plenty of time for all sorts of interactions between galaxies to have happened many, many, many times. And so maybe a lot of the spin has to do with the interactions rather than with the gravity. That's just one idea that occurs to me off the top of my head. But again, I think that if we want to explain why the galaxy looks the way it does, and honestly, if we even want to explain why stars look the way they do and so forth, we either end up having to invent something somewhat magical, or we have to think outside of the idea of gravity being the central player, or the only player, let's say. Certainly gravity is important, but I don't think it's the full story. All right, so anybody have any more questions over this amount? So this is what I'd hoped to get through during our snow day. So I'm going to just start what I was going to get into today. So we're going to move in and talk a bit more about galaxies in general, not just our galaxy, but other galaxies as well. Because essentially we're going to take what we learn about our galaxy and apply it to everything else. This is, of course, Andromeda, which is the most beautiful and close galaxy to us. This was the one that was at the center of the debates with Hubble and so forth. And Hubble actually was able to resolve this galaxy eventually with his multimeter telescope. Now, I mentioned before that Hubble was actually able to observe the variable stars and calculate the distance, which he estimated to be something like 900,000 light years away from us. Now, bear in mind, our Milky Way itself is something like 80,000 light years across, all right? So there was no way this thing could be inside of our Milky Way, according to his calculations. And actually, it turned out that Hubble, everybody at the time had confused these variable stars. There's actually 2 different types of variable stars, and it was sort of smearing out their measurements. And ultimately, it turned out that they were off by a factor of 2. So Andromeda turned out to be actually twice that distance away. So the distance between galaxies is hard to comprehend. If comprehending, I mean, it's difficult to comprehend what a light year, how long that is, right? But suffice to say that the distance between us and the outer boundary of the next star system is at least a few light years away, right? I mean, that's a distance that's incomprehensible. But now you think about the length of our Milky Way being almost 100,000 light years, and then the distance to another galaxy being millions of light years away. It's just, it's unimaginable, right? I wonder, it's inconceivable to me in our technological paradigm today that we would ever be able to experience another galaxy, because the idea of traveling for millions of years to get somewhere, even at speeds close to light, is just beyond my imagination. But who knows what we'll come up with later. All right, so there's a few different types of galaxies, actually, when we look out there, and we can class them together, essentially. Now, unfortunately, the way that this is drawn, you might get the impression that they're kind of on an evolutionary continuum, but it doesn't seem like that works out, unfortunately. And we can talk about why that is as we go through this. But this is actually the classification scheme that Hubble came up with. The names are a bit perplexing. I don't expect you to remember any of these. But essentially, you have spiral galaxies, and the spiral galaxies are more or less divided by the presence of a central bar or not, although the bar is like a very poorly understood phenomenon. We'll play with that a little bit. So let's look at these a bit. So this is actually a galaxy called M100, and we can see the spiral here. And if we look edge on, we actually see that there's a fair amount. Well, this isn't a great picture for you, but you can see actually that there's a little ring of darkness there. All right, this is all of that dust that's in the outer regions. So there is a lot of non-luminous matter out there. So this galaxy, our own galaxy, and Andromeda, they're all typical large spiral galaxies. They have this central bulge, the halo, the disks, spiral arms, all of that. And the interstellar matter is usually spread throughout the disks. There's bright emissions from the young stars that are present in those, especially in the spirals, where we expect to see new stars being formed. The bars are quite interesting. So the bars are thought to form when the stellar orbits in a spiral galaxy become unstable and sort of deviate from their circular path. So you can imagine as the inner stars are making their way around the central region of the galaxy, they get somewhat hung up. They sort of start to interact with one another, and they pile up there to some extent. So it's interesting because both the span of the galaxy and the mass seems to play in to determining whether a bar is even present and how big it is, which, again, it's not a situation where some galaxy is going to evolve into a bar galaxy that didn't have one before. It seems to really have to do with the starting conditions, at least under the present theory. So those are our two main layouts. Now, you also have this other kind of galaxy. For some of these smaller galaxies, you have galaxies called ellipticals now, or ellipsoids. So these galaxies are mostly older reddish stars, population 2 stars, and they're very tricky to study because the stars that are in these elliptical galaxies are all orbiting in different directions, right? It gives us this makes it very difficult for us to do the kind of radial velocity calculations of the distance that we were talking about before. So these are a bit harder to study. We do suspect that they're older since they are almost all reddish stars. So then we also have irregular galaxies. Irregular galaxies have lower masses and lower luminosities than the spiral galaxies. And they're very disorganized, much like the elliptical galaxies, but they seem to have both young and old stars in them. And the best examples that we have are those Magellanic clouds that we were talking about earlier. And you can actually see these things off here with the Milky Way and the little Magellanic clouds. I'm not sure where this photograph is from. Somewhere high on a mountain somewhere. And so they sort of trail debris behind them. You know, there's not a great evolutionary model for how these irregular ones form, but again, they seem to be the products of interactions with galaxies, right? They seem to have been torn apart somehow, which is quite interesting. All right. In terms of calculating the masses of galaxies, this is a little bit tricky, but it's basically the same idea that we use to measure the masses of, say, distant stars that we've been talking about. And essentially what we do is we assume that the speed of how the objects in the outer regions orbit the center is proportional to their gravitational attraction. Now, this is a weird method to apply because we know that it absolutely isn't the case that the speed is an appropriate output of the mass, right? Unless we put in this missing material, which we call dark matter. So the masses that we derive from galaxies have to do with their rotational dynamics, which we assume are gravitational, but at the same time, we know that they're definitely either not gravitational or there's a lot of this dark missing material, right? Dark matter. So I don't know. Take these mass estimates with a grain of salt, but you know, essentially we come up with the idea that most of the galaxies are enormous. This one, actually, M101 here, we have pictured here, it's actually about twice the diameter of the Milky Way, and it contains something like 1 trillion stars by this method. And actually, the mass ranges fall out based on the different types of galaxies you see here. So you can see, actually, I have to look at this. So essentially, the spirals tend to be the really big ones, right? There are extremes, but the mass distribution seems to follow to some extent. We can also look at the light ratio, which is interesting. So an interesting way of characterizing a galaxy is checking out this ratio of how bright it is to how much stuff is there. And that story, what that ratio is going to essentially tell us what kind of stars make up the most luminous portion of it. And then they're also going to indicate how much of the gravitational effect is unaccounted for, i.e. dark matter, or not gravitational. So by definition, the mass to light ratio, we call that 1 for our star, 1 unit of mass, 1 unit of light. Now, the mass to light ratio for low mass stars is more than 1, which makes sense. Now, if the mass to light ratio is greater than 1, well, for a galaxy's mass to light ratio to be greater than 1, it depends on the ratio of high mass stars to low mass stars. So galaxies where star formation is still occurring have a lot of massive stars. But so their mass to light ratios are somewhere between 1 and 10. The ones that have older stars, like the ellipticals, turn out to have mass to light ratios of 10 to 20. You can sort of see that fall out in this story here. Now, where we're headed from here is one of the biggest questions in astronomy, which is how to gauge the distances to these stars. And I think that is a really good place to stop for now, because we're going to take that and construct a cosmology based on it and based on the motion of these distant galaxies. So anyways, I hope you guys have a good week, and we will pick up with our cosmological pursuit next time.